We present our paper titled Learning from Extrinsic and Intrinsic Supervisions for Domain Generalization. Domain generalization for object recognition aims to train a classifier on multiple source domains so as to generalize to the unseen target domain. Existing domain generalization methods on object recognition consider distribution alignment or network regularization. Well, we argue that a generalized object recognition system should well understand the relationships among different images and also the images themselves at the same time. To this end, our method aims to learn how to generalize across domains simultaneously, from extrinsic relationship supervision and intrinsic self-supervision for images from multi-source domains. To deal with the object recognition, we first train a common classification network, including an encoder F and a classification head H. To broaden the network understanding of the object, we employ the recently proposed solving jigsaw puzzles as our auxiliary task. The auxiliary self-supervised task is able to exploit the intrinsic semantic information within a single image to provide informative feature representations for the main task. Then, we design a momentum contrastive learning scheme to encourage the network to learn such domain-independent yet class-specific features by considering the mutual relation among samples across domains. Specifically, we introduce a momentum-updated encoder to extract consistent embedded features. We store these object features into a memory bank with a large bank size. We dynamically update the memory bank by discarding the oldest items and feeding the new batch of embedded features, where the memory bank acts as a queen. We design a key-hard negative selector for triplet selection. Given an uncode sample, we choose a corresponding positive sample with the same class, and select k negative samples from the memory bank with different class. We then optimize the triplet loss for extrinsic supervision. The goal of the original triplet loss is to assign close distance to pairs of similar samples, that is, positive pair, and long distance to pairs of dissimilar samples, that is, negative pair. Selecting informative triplets could benefit the network learning, especially the negative samples. The random selector only randomly selects one negative sample. Since the selected negative sample may already obey the triplet constraint, the training with random selector may not be efficient. The semi-hard selector is to select one informative negative sample, which do violate the triplet loss constraint. Well, we propose a novel k-hard negative online selector which extends the triplet with k negatives that violate the triplet constraint. We show an example in figure C when k equals to 2. Our k-hard negative selector for triplet loss is obey the constraint t prior to select triplets. The objective function LT prior is to minimize the distance between uncode and positive sample and maximize the distance between uncode and negative sample. The momentum encoder parameter theta j is updated as a moving average of encoder parameter theta f. For more details, please read our paper. We compare our method with other methods on two benchmark datasets. Moreover, we include the within-domain performance of all the datasets as a comparison to reveal the performance drop due to domain discrepancy. From the result tables, we observe that our EISNet achieves best average accuracy over 4 domains on two benchmark datasets. Then we compare our method with baseline method, DeepL, and the state-of-the-art method, MASF, using ResNet 18 and ResNet 50 backbones. Our method consistently outperforms MASF, about 1.11% and 3.17% on average accuracy, with ResNet 18 and ResNet 50 backbones, respectively. Note that the improvement over MASF is more obvious with a deeper network backbone, showing that our proposed algorithm is more beneficial for domain generalization with deeper feature extractors. We conduct extensive analysis of our method. We investigate the effectiveness of extrinsic and intrinsic supervisions on the PCS dataset. We observe that each supervision plays an important role in our framework. By combining extrinsic and intrinsic supervisions, performance is further improved across all the settings, indicating these two supervisions are complementary. We also analyze the best number of negative samples and momentum parameter data. It is observed that the network performs well when data is relatively large. A small data would degrade the network performance, suggesting that a slow updating momentum encoder is beneficial to the feature consistency. The size of memory bank M can be adjusted according to different tasks. Our method is able to generate better results with a large memory bank size and negative samples. To validate the effectiveness of keyhard negative selector in our proposed metric learning, we compare our proposed keyhard negative selector with original random triplet selector and semi-hard negative selector. The results demonstrated the effectiveness of the proposed keyhard negative selector. Apart from the performance improvement over other methods, our method has much lower computation cost. Under the same server setting, one Titan XP GPU and AlexNet backbone, our method could save more than 91% time cost on training phase compared with the MASF. We also employ t-SNE to analyze the feature-level discrimination of our method, and the visualization results are shown in figure right. Compared with the feature extracted from the ImageNet pre-trained network, the distance between different class clusters in our method becomes evident. To conclude, in this paper, we present ERSNet, a domain generalization method that considers both extrinsic and intrinsic supervisions. And extensive experiments demonstrated the performance improvement on VLCS and PACS datasets, especially on deeper backbones. The code is available online. Welcome to contact us to discuss more details. Thanks.